Friends, welcome back to my YouTube channel. In this class, I am going to discuss 3 more problems of chapter 7 of PKNAG's Engineering Thermodynamics, which are based upon the concept of entropy and entropy generation. Before starting, I must say one thing to all of you. Please do subscribe to this channel. Of course, like it and share it to your friends. You see, the question number 7.16 is like this. In the temperature range between 0 degrees Celsius and 100 degrees Celsius, a particular system maintained at a constant volume has a heat capacity capital CB. In fact, this is the product of mass and specific heat at constant volume MCB, small cb, and it is a function of temperature, especially between the temperature range of 0 and 100 degrees Celsius. So A plus 2B multiplied by T. The value of A is given 0.014 joule per Kelvin and B is 4.2 multiplied by 10 to the power minus 4 joule per Kelvin square. And heat reservoir at 0 degrees Celsius and reversible work source are available. What is the maximum amount of work that can be transferred to the reversible work source as the system is cooled from 100 degrees Celsius to the temperature of the reservoir? So, system is at temperature of 0 degrees Celsius. Suppose this is your system which is at temperature T1 and the heat engine will produce work only to the point when the system's temperature goes down to T0, the temperature of the reservoir. In this case, this T0 is 0 degrees Celsius and T1 is 100 degrees Celsius. And capital CB is equal to A plus 2BT. A is 0.014 joule per Kelvin and B is 4.2 multiplied by 10 to the power minus 4 joule per Kelvin square. So this is some heat is going to the heat engine. This is heat engine is there which produces work, and this is the heat input, Q is the heat input, and if the heat engine produces W, net work output, then Q minus W is the heat rejected to the thermal energy reservoir, that is low temperature thermal energy reservoir, which is at a temperature of T0. Here T1 is 100 degrees Celsius. It is written in the last sentence of the question, 100 degrees Celsius. And in terms of Kelvin, this will be 373 Kelvin. And T0 is 0 degrees Celsius. This is 273 Kelvin. So we have to find out maximum work done. You know, maximum work is done when all the processes are reversible, and we can calculate the maximum work by applying the principle of increase of entropy. In fact, this principle is delta S universe is greater than or equal to 0, and it is equal to 0 when all the processes are reversible. So we have to find out delta S universe. Delta S universe, how can we find out? We have to, there are three parts of this universe, the composite system. One is system, another is reservoir, and another is heat engine. Delta S of heat engine is going to be 0 because heat engine completes a cyclic process. So we have to find out a change in entropy of the system as the system cools down to temperature T0, and the delta S of low temperature reservoir also we are to calculate. So for that, first we have to find out what is the value of Q. So you see, heat removed from system is equal to Q is equal to capital CB dt. Limit is from T0 T1. And an important thing you must know, that if you were to find out what is the heat transfer, then T1 would have been the lower limit and T0 would have been the higher final limit. Initial limit would have been T0 and final limit would have been T1, because the initial temperature is T1 and the final temperature here is T0, and answer would have come out in terms of negative because the heat is discharged or heat is rejected from the system. But we are here calculating heat removed from system, and if you want to calculate this heat removal, then T0 has to be in the lower limit and T1 is in the upper limit, and answer would come out in terms of negative because we are calculating heat removal from system, so it will come out in positive. If we had calculated heat transfer of the system, it would come out negative, and one would simply understand that heat is discharged from or heat is removed from the system. So this is Cv, integral of Cv dt. This is equal to A plus 2bt dt. Limit is from T0 to T1, and this is equal to A dt plus 2b T dt, because 2b is a constant, it can be taken outside. So T0 to T1, this is also from T0 to T1, and this becomes a T1 minus T0 plus 2b T square by 2 T0 to T1, and on calculating this comes out to be 0.014 100 plus 4.2 multiplied by 10 to the power minus 4. These values are given. B is 4.2 into 10 to the power minus 4. 2 cancels out. So that's why 373 square minus 273 square, this equal to 28.532 joule. This is the heat removed from system. So now we will calculate the delta S of system, then delta S of reservoir will also calculate, so that we will be in a position to calculate delta S of universe. So delta S system is equal to Cv dt by T. Limit is from T1, initial temperature is T1 and final temperature is T0. So Cv dt upon T, this is equal to A plus 2bt divided by T dt, T1 to T0, and this is equal to A by T plus 2b dt. Limit is from T1 to T0. This is equal to A ln T0 by T1 plus 2b T0 minus T1. This is coming out to be, so 0.014 ln 273 by 373 plus 2 into 4.2 into 10 to the power minus 4. This is 273 minus 373. This is coming out to be minus 0.0884 joule per Kelvin. This is delta S of system. Now delta S of TER, thermal energy reservoir. You see, I have already calculated, we know how to calculate the delta S of thermal energy reservoir. This is the heat supplied to thermal energy reservoir. But during the heat addition to this thermal energy reservoir, its temperature does not change. So this delta S of TER will be nothing but Q minus W divided by T0. Q minus W divided by Q minus W divided by T0. T0 is the temperature of low temperature reservoir. So, and delta S of heat engine is 0 always, because it is a cyclic process, and cyclic integral of any property is 0, and entropy, as you know, is a property of system. So delta S of heat engine is 0. So delta S universe is now minus 0.0884, that is delta S of system, minus 0.0884 plus delta S of reservoir is Q minus W max divided by T0. And this is especially when W is maximum work, means the processes are reversible, and for reversible process delta S universe is equal to 0. So from this equation, you know, from principle of increase of entropy, when all the processes are reversible, maximum amount of work is produced. So from this, in place of W, if we put W max, this would correspond to 0, because delta S universe for a reversible process is 0. And so from this equation we can find out W max, because we have already found out the value of Q. So 28.532 Q you have already calculated. Q is 28.532. So Q minus W max divided by T0 is 273 minus 0.0884 is equal to 0, or 28.532 minus W max by 273 equal to 0.0884. From this we can calculate the W max. So W max will be 4.39 joule. 4.39 joule. So this is the answer. So maximum amount of work that can be transferred to the reversible work source as the system is cooled. So this is the maximum amount of work that can be obtained, and this is obtained in case of reversible process when delta S universe is 0. So next question is like this. 7.17. So each of the two bodies has a heat capacity at constant volume, that is Cb is equal to A plus 2Bt. This is a case when there are two bodies, two finite bodies, and each is having heat capacity or product of mass and specific heat at constant volume, that is Cb is equal to A plus 2Bt. A and B, values of A and B are given. If the bodies are initially at temperatures 200 Kelvin and 400 Kelvin, and if a reversible work source is available, what are the maximum and minimum final temperature to which the two bodies can be brought? What is the minimum amount of work that can be, maximum amount of work that can be transferred to the reversible work source? So the same type of problem as we solved in 7.16. Only difference is that in that case a reservoir was there. In this case there are two bodies, two finite bodies. So suppose one body had that body with higher temperature is 400 Kelvin. So body A, suppose its initial temperature is T1, and there will be a common temperature to which both the bodies will be brought in. If the bodies are initially at this temperature and the reversible work source is available, what are the maximum and minimum final temperatures to which the two bodies can be brought? So that temperature will definitely lie between 200 and 400 Kelvin. The temperature of the body, that is 400 Kelvin, that is the high temperature body, its temperature will go down, and the temperature of the low temperature body will go up. So the final temperature will lie something in between. So you have to find out that final temperature, especially when the maximum amount of work is produced. So this is a body B. Its temperature will also go up from T2 to T, and the temperature of this body will go down from T1 to T. So let heat supplied to the heat engine is Q1 and the work produced is W. Suppose heat rejected to this body B is Q2. So Cb is given A plus 2Bt. A is 8.4 joule per Kelvin. B is 2.1 multiplied by 10 to the power minus 2 joule per Kelvin square. T1 is 400 Kelvin and T2 is 200 Kelvin. So as we are required to find out what is the common temperature T, especially when maximum amount of work is produced. So for maximum amount of work to be produced, all the processes are to be reversible, and for that case delta S universe has to be 0. So that means delta S of body A plus delta S of heat engine plus delta S of body B has to be 0. And you know delta S of heat engine is 0 because it is a cyclic process, and cyclic integral of any property is 0. So we have to solve this equation. So you see delta S of body A, it is equal to Cv dt upon T, and the initial temperature is T1 and final temperature is T. So this is equal to A plus 2Bt by T dt. Limit is from T1 to T, and this is equal to A is a constant, so A dt upon T, T1 to T plus 2B, 2B T divided by T, that is cancels out, and now this is the 2B dt T, and this is T1. This is equal to A ln T upon T1 plus 2B T minus T1. This is the delta S of body A. So delta S of body 2 or body B, that will be A by T plus 2B, because the Cb for both the bodies is same function, A plus 2Bt. So A by T plus 2B, and this process will stop, and this process of production of work will stop only when both the bodies come to a final common temperature, because these are finite bodies, these are not infinite bodies that the engine will continuously produce work. Since these two bodies are finite bodies, the process will stop working once the final common temperature is attained by both the bodies, but T will be less than T1 and greater than T2. So delta S body B of body B will be A by T plus 2B dt, and this is T2 is the initial temperature and T is the final temperature. This is equal to A ln T upon T2 plus 2B T minus T2. So delta S universe will be delta S A plus delta S B only. So this equation will be A ln T by T1 plus A ln T by T2 plus delta S of A plus delta S of B plus 2B T minus T1 plus 2B T minus T2. And in this case, for maximum work, delta S universe has to be 0 according to principle of increase of entropy. Now just we have to solve this equation to find out the temperature T, or 2A, this is A ln T square by T1 T2 plus 2B 2T minus T1 minus T2 equal to 0, or A ln this is T by square root of T1 T2 square plus 2B 2T minus T1 minus T2 equal to 0. Ln x square is equal to 2 ln x, or 2A ln T upon square root of T1 T2 plus 2B 2T minus T1 minus T2 equal to 0. On dividing both terms of this equation by 2B, we get A by B ln T divided by square root of T1 T2 plus 2T minus T1 minus T2 equal to 0. And putting the values of A and B, 8.4 by 2.1 multiplied by 10 to the power minus 2 ln T by square root of 400 multiplied by 200 plus 2T minus 200 minus 400 equal to 0. On solving T by trial and error method, T will come out as 292.9 Kelvin. So this is the minimum temperature in fact. So temperature will be minimum only when maximum amount of work is produced. So this is the minimum temperature to which these two bodies will come. So if you want to calculate W max, so W max can be calculated like Q1 minus Q2, Q1 minus Q2. So Q1 minus Q2. So Q1 and Q2 can be calculated once you are able to find out the temperature T. So we have already calculated value of T. So we can calculate Q1 and Q2. So Q1 will be, you see, Q1 will come out as integral of CB dt, and limit is from T to T1. This is in fact the Q1. So this is equal to 2455.97. This is heat removed from the body A. So similarly Q2 can also be calculated, CBDT. This is the heat added. So in fact the initial temperature will be T2 and the final temperature is T, and this is coming out to be Q2 is 1744.029. For by putting the values of T as 292.9 here, value of T will be taken to be 292.9. So once we have calculated Q1 and Q2, so W max will be Q1 minus Q2, because you see according to first law of thermodynamics, if we are W max, sigma W cycle is equal to sigma Q cycle. For this cycle, Q1 is the heat input and Q2 is the heat output. Heat added is Q1 and heat rejected is Q2. So Q1 minus Q2 is the W. So that means W max is Q1 minus Q2, 2455.971 minus 1744.029. this is equal to 711.942 kilojoule. So next question is 7.18. 7.18. So 7.18. A reversible engine, as shown in figure, during a cycle of operations draws 5 megajoule from 400 Kelvin reservoir and does 840 kilojoule of work. Find the amount and direction of heat interaction with the other reservoirs. In fact, there are 3 reservoirs. One is at temperature 400 Kelvin and second one is at 300 Kelvin and another is at 200 Kelvin. Q2 and Q3 are the heat interactions with these 2 reservoirs, but we have to find both magnitude and direction from this, and obviously this is a reversible engine. So we will first assume the directions and later on we will check it whether it is correct or not. Suppose we will take Q2 as heat coming to heat engine, and Q3 also heat coming to heat engine. So this is our assumptions. So later on we will check it whether our assumptions are correct or not. If Q2 and Q3 comes out to be negative, then its assumed direction will be reversed to find out the correct direction. So this is 200 Kelvin. Suppose this is the direction of Q3 and this is 300 Kelvin. So this is the direction of Q2 and this is heat engine, and this produces 840 kilojoule, or you can say 0.84 megajoule, and another reservoir from which heat comes to the heat engine is, this is Q1. This is given in the question, 5 megajoule. Because you see, if you read the question, you see during a cycle of operations draws 5 megajoule from 400 Kelvin reservoir. So now Q2 and Q3 both magnitude and direction are to be obtained. This is our assumed directions. All heat interactions are coming to the heat engine, only work interaction is going out of the engine or work is produced. So according to first law of thermodynamics, sigma Q cycle equal to sigma W cycle. So here all heat interactions are towards the heat engine. So Q1 will take all the heat interactions towards the heat engine as positive and away from the heat engine as negative. By convention we are taking this. So Q1 plus Q2 plus Q3 is equal to, these are the energy coming into the system, coming into the heat engine, and this energy is going out of the heat engine. And for a cyclic process, E in summation of E in is equal to summation of E out. Energy cannot be energy can neither be created nor can it be destroyed. So whatever energy is coming into the system during cyclic process must go out of this, so that there is no accumulation of energy within the system. So Q1 plus Q2 plus, since this is a cyclic process, Q2 plus Q3 is equal to W. So Q1 is already given to be 5 megajoule plus Q2 plus Q3, and this is W is 0.84 megajoule. So this is 0.84 and in this side the Q1 is also 5. We have converted this 840 kilojoule to megajoule. Now Q2 plus Q3 is equal to 0.84 minus 5, that is minus 4.16, and this is megajoule. and this is equation 1. This is equation. And according to Clausius inequality, according to Clausius inequality, according to Clausius inequality, we know that Clausius inequality, which is valid for cycles only, cyclic integral of del q by t is less than or equal to 0, and in fact cyclic integral of del q by t equal to 0 for reversible cycle. So here this is a case of reversible heat engine. So, and heat added to a system while calculating del q by t, heat added to a system will be taken to be positive and heat rejected from the system will be taken to be negative. So Q1 by 400, because you see Q1 is coming from 400, this reservoir whose temperature is 400 Kelvin, plus all heat are coming to the heat engine, Q2 by 300 plus Q3 by 200 is equal to 0, because this is a reversible cycle. So, or Q2 by 300 plus Q3 by 200 is equal to minus Q1 by 400, and this Q1 is 5 megajoule. So, minus 5 by 400. On equating, you see this is 600, 2Q2 plus 3Q3 equal to minus 5 by 400. So this becomes 8Q2 plus 12Q3 on cross multiplication. This becomes minus 30. So this is equation 2. Now we are having two equations and two unknowns. You see, this is the first equation, Q2 plus Q3 is this much, and 8Q2 plus 12Q3 is minus 30. So on solving equations 1 and 2, we get, so this is on multiplying equation 1 by 8, 8Q2 plus 8Q3 equal to minus 33.28, and this equation is 8Q2 plus 12Q3 equal to minus 30. Subtracting equation 2 from equation 1, we get 8Q2 minus 8Q2 cancels out, only minus 4Q3, 8Q3 minus 12Q3 minus 4Q3, this becomes minus 3.28. Q3 is plus 0.82 megajoule. So whatever directions we have assumed is correct. So definitely Q3 is coming into this heat engine. Q3 we had assumed that Q3 is coming to the heat engine from reservoir. So Q3 is coming to the heat engine. There is no problem in it. Now we'll check whether Q2 is coming positive or not. By substituting the value of Q3 in any of the two equations, we will get Q2 plus 0.82 equal to minus 4.16, from which Q2 is equal to minus 4.98 megajoule. So Q2 minus Ri, matlab the direction we had assumed is not correct. We had assumed that Q2 is coming towards heat engine, but this is not correct, and the correct direction is the heat is going away from heat engine, or heat is being rejected to this 300K reservoir from heat engine. So the correct diagram will be like this. This is correct diagram will be so in fact the correct diagram will be like this. Q3 is okay, Suppose correct diagram will be like this. This we had assumed, so this is correct. Correct will be like this. But Q2 we had assumed in this manner, but correct will be like this. And Q1 is given. So in this, the diagram will be like this, correct one. This is Q3, but this will be like this. And you can check it also. What is the summation of energy that is coming into heat engine? 5, and this Q3 is 0.82. So 5.82, and this one is, what is the amount? Q2 is coming out to be 4.98. So what is the summation of energy entering into the heat engine during the cyclic process? 5, one is 5 and another is 0.82. On adding 5.82. And what is the summation of energy that is leaving this engine during this cyclic process? One is 4.98 and another is work. Here also the arrow sign is away from the heat engine. That means this energy is leaving the heat engine during the cyclic process, and this energy is also leaving in the form of heat. So if you add 4.98 and this is 0.84, this is also coming out to be 5.82. So this obeys the first law, this satisfies the first law of thermodynamics. So the correct magnitude will be Q3 will be 0.82 megajoule and Q2 will be 4.98 megajoule, and direction will be like this. Q3 will be heat coming from this 200 Kelvin reservoir, and Q2 will be the heat rejected to this 300 Kelvin reservoir. Heat will come from both these two reservoirs are source. This 400 Kelvin and 200 Kelvin, and one is the sink, that is 300 Kelvin. So that's all. Thanks for watching.